Okay, let's look at the relationship between delta H and delta E. What really is the difference? Well, the difference is whether any work is done is the short answer. So the delta H equals delta E plus P delta V. That is, you have to adjust for whatever work's done. A lot of times in chemistry, the work term is negligible, so those two are roughly equal to one another. Remember, the delta H is the change in enthalpy of the system, delta E is the change in internal energy, and P delta V refers to the work being done in a pressure volume sense. Usually that work term for an ordinary reaction is pretty close to zero, because the volume change is pretty close to zero, because you just got a container open to the atmosphere and the gas can escape into the bulk of the atmosphere. So P delta V is zero, which means the work term is zero, which means that delta H is approximately equal to the delta E. If the volume change were exactly zero, they would be equal. And that's the assumption, at least at this level of chemistry, that most people make, is that work term is zero most of the time. And we'll do some examples and show you why that is. So we use that as a general rule and use delta H, or the enthalpy or the heat of reaction, instead of delta E. And the main difference is the amount of work done by the system. Now, if you wanted to calculate the delta E, you could use something called a bomb calorimeter, which ensures constant volume. Delta H turns out to be the heat at constant pressure, but the heat at constant volume would give you the delta E. In this system, a lot of times this rigid constant volume system is used for heat of combustion. You put the substance in that little cup, measure the temperature change of a very specific amount of water, ignite it with those wires, stir the water to ensure the heat distribution. You'd measure the temperature difference of that, and then that you could calculate your heat that way. So let's justify that to ourselves and say the enthalpy of combustion of pentane is C5H12 is negative 3523 kilojoules per mole. We burn 1 mole of pentane at constant pressure. That means it releases the 3523 kilojoules of heat. We will know the work term and the delta E for the reaction at 298 Kelvin. Okay, let's look at this problem. I've copied the reaction and the delta H from the question text. Now, what you have to realize is that we need the delta N for this. That's a liquid, so we're talking about 8 moles on the reactant side. And over here, sorry, that's a gas. That's a gas. So we got 11 moles on the product side. So the delta N for the process is 3 moles. Now, let's look at our formula. Delta E is going to essentially be our delta H plus our work term, where delta H is our heat. Instead of Q, we're writing delta H. So plugging in delta E is going to be the negative 3523 kilojoules minus we're going to have to get work, we're going to have to use minus delta nRT. So we're going to minus 3 moles. Instead of the P delta V, we can say minus nRT. We set that equivalent in our previous video. Now, the version of the gas law constant we're going to want for this is 8.314. Now, we're going to have to say times 10 to the third here, or 10 to the negative third kilojoules per Kelvin mole to make the units work out. Normally, R is 8.314 joules per Kelvin mole. I'm just converting it to kilojoules so that we have matching units. And then our T is 298 Kelvin. So in that case, our delta E becomes a negative 3,530 kilojoules. So if you compare the two numbers, we're only talking about 7 kilojoules of difference because of the work of the gas is pushing on the atmosphere at large. So a lot of people say that amount is negligible and therefore just ignore it. And so we just assume that delta E is approximately equal to delta H because the work term is so small.